Okay, I'm going to start with Canvas, where we are, where we're going, and what have we done. This is Monday B Day. This is talking about the beginning of this week. Last week we were Friday A Day, and you can see work 1, work 2, work 3. Those worksheets, those are now due. Not due like this minute, this class period, but before next class. On Monday we have an FRQ and review. On Tuesday, that's Monday, Tuesday, and then on Wednesday we have our test. So we need to have all of the practice work, all of the homework done before then so that we understand what do we know, what do we not know, how to fill in the gaps. So you can look at this week's Canvas and see what Friday had listed because A Day and B Day are duplicates as far as regular class days. Work 1, work 2, work 3, those are all coming due. Tuesday, Wednesday, you had work energy theorem that some questions were coming through, and I've kind of just given you a little bit of information because I'm going to be posting the key between today and tomorrow, probably more likely tomorrow, but that gives you an opportunity to look on how to work those. And also I need to encourage you to take advantage of tutorials. We have them every morning and every afternoon except Monday morning and Friday afternoon. That means you have after school today and before school tomorrow, and that's the last of the tutorials before your FRQ on Monday. Now we come down to Thursday, Friday. There's a concept check listed. That concept check is due at the end of day tomorrow. Now, don't go find someone that's just going to hand you all the answers because I don't care what you get. I'm not even going to look at your individual score. I want to look at the class scores on the individual questions. I want to see if a question is missed more often than not. I want to see what wrong answer was the most popular wrong answer. I want to see a survey of the questions, not individual performance. I won't even look at your individual performance. It won't show up as a grade. Do the best you can because it helps me understand what you know and how to teach you better. So please approach it in that fashion. Please have it done by end of day Friday. Those next 3 files, the Kinematics review, the one that says notes, the one that says notes, we're going to do all of that together except for one problem across all 3 sheets. I'm going to leave one problem for you to do. That means that between now and the next time we're in class, the only thing I'm assigning you to do is one problem from today and all the homework, catch it all up. That's it, okay? Just catch your stuff up. If you've been doing work, you got less to worry about. Don't forget that today is Friday, 5 o'clock today, retests are over. So get that done, and sometime between now and Friday night sometime, I'll do my best to get the retest scores brought over. You'll know that your retest score has been brought in when you see that your original test score has a decimal grade. Your original test score will be the decimal grade. The number before the decimal will be your new score. The number after the decimal will be the original test score. Let's see, I've got some things flying through the chat. Will the test have FRQs? Yes. So you have FRQ Monday and FRQ Wednesday. But I think the FRQ on Monday is turning more into like a quiz-like format and not written. But Wednesday, I think definitely will have writing components. Next Monday, it says FRQ practice. Is that a grade then? Yeah, it was called FRQ practice because the document that we were pulling from was called FRQ practice, but now it's being made custom. So you'll see that the description on that changes. My computer's glitching. Can I log in through another computer? Yeah, go for it. I'll admit you. I mean, what's the worst thing that happened? You just bomb us. We'll all laugh about it. I'll get in trouble. And then, you know, it's going to be funny. So that's cool. Is the test grade going to be conceptual based more on math since we've been practicing math based? That's a good question. I have it in front of me, but I haven't looked through it and we haven't built it into Canvas. So we try to do a blend. I'll know more Monday, probably, maybe, perhaps. I don't know, we'll see. Right now, I can tell you that your FRQ would be the last problem we do together today. Get good at it because your problem on Monday, not based on the same thing, but the tools and the concepts will all be there. Cool. All right, let's take a look at today's work. We're going to start off a little bit easy, which is great, but then we're going to pick up intensity as we go along. All right, this is going to give us a description of kinematics and energy. Let's see if we can put our brains back in kinematics mode. As much as we all loved kinematics, we were happy to see it go, but it keeps rearing its ugly head. Let's see what the information given to us is. The initial velocity is 6 meters per second. So our V naught equals 6 meters per second. How high will the gazelle go? Let's see, when it goes up at its maximum height, the velocity equals 0. Acceleration's due to gravity going down. It's bringing the gazelle back to its original position. So that would be negative 10 meters per second square. And we're looking for delta y. Delta y equals question mark. We dig back through our notes. We try to find that formula that basically has no time. Didn't ask us anything about time. So no time. And then the formula that had no time was v square equals v naught square plus 2a delta y, something like that, 2a delta y. Okay, so that's the formula that gives us that information. We want to solve the formula for delta y. What I'm going to do is I'm going to subtract both sides by v naught square, divide by 2a. That will get delta y by itself. So we would have v square minus v naught square, let's see, divided by 2a. That seems reasonable, equals delta y. Okay, so if this was your AP1 exam, we would be done. All variables, right? But we have numbers. V square, V is 0, so 0 square is still 0, minus 6 square, negative 36, divided by 2a. A is negative 10, two of them would be negative 20, is equal to delta y. I'm gonna put this in a calculator just to make sure I'm not going crazy. 36 divided by 20. I don't want silly math mistakes. I get 1.8 meters equals delta y. Awesome. We knew how to do that. We did that months ago. How long will the gazelle be in the air for? I've got the same variables, but now I have more information. V naught equals 6 meters per second. Final velocity equals 0 meters per second. Acceleration is still gravity, negative 10 meters per second square. Delta y we solved for equals 1.8 meters. And then now we want to know time. Well, I've got 4 known variables. I can choose which one that I kind of push aside and pick a formula based on it. Since I calculated delta y, perhaps I don't trust myself. Perhaps I'm like, hey, I can make mistakes. I mean, we all make mistakes. So if I say I had no delta y, we could use VOTAT. V equals VO plus AT. We want to solve this for time. I'm going to subtract both sides by V naught and then divide by A. V minus V naught divided by A equals time. Use our variables to plug things in. I've got 0, which would be, let me let our crasher in, there we go. I've got 0 minus 6, so that's negative 6, divided by negative 10 equals time. So in this case, we say that time would be 0.6 seconds, but we know that's time to the top because we base this off of V final velocity being 0. That's at the top. The question said for total time in the air. So if it is 0.6 up, it is 0.6 down. Total time would be 0.6 times 2 or 1.2 seconds. See, we can remember kinematics. Wasn't so bad. All right. Then what about energy? Okay, we can do that. All right, how high would the gazelle go? When the gazelle's on the ground, he has no height, but he has velocity. That means he's got kinetic energy on the ground. As he jumps, he's going to slow down, but he's going to gain height. That kinetic energy will become gravitational potential. Will we use change in kinetic formula for this? Well, we're not looking at a change in kinetic energy. We're looking at a conversion of kinetic energy to gravitational potential. What we should see is 1/2 mv square is at the beginning is going to be equal to mgh when we get to the top. So we're going to say it's equal to mgh. So I would draw you a gazelle, but it would just be for fun. But what I say is that the kinetic energy at the beginning of his jump is equal to the gravitational potential at the highest point of his jump. When his velocity goes to 0 and he has no more kinetic energy, that's the point that he has the highest height, which would give him the greatest gravitational potential. All the kinetic has now become gravitational potential. Full conversion. If we see that, within the formula, we can cross out mass. It's in the same place. I want to solve for height. I'm going to rearrange this so it's equal to height. To do that, I need to divide both sides by gravity. I would have v squared over 2g. That is equal to the height. Now I can use the numbers they gave me. Velocity is 6, so 6 squared is 36, divided by 2g. If g is 10, 2 times 10 is 20, equals h. And 36 divided by 20 should be 1.8 meters, equals the height. I was able to use kinematics, and I was able to use energy to solve the same problem. I know energy makes things so much better than kinematics. Why, oh, why didn't we start with that? Why did you not use 0 for velocity? Because in the beginning, he had kinetic energy, and that kinetic energy was transferred to gravitational potential. All right, I'm going to make fun of myself. All right, you can all laugh. Here is my gazelle. All right, this is homecoming day, so he's wearing his, what is this, a mum? All right, it's wrapped around his neck, so he's sad because no one wants to wear those things. And my gazelle has, those aren't antlers. What are the things that moose have? Are those antlers? Yeah, they're still antlers, whatever. So he's got a leaf-looking antler. Okay, so there's my gazelle. He's leaping upwards at a velocity of 6 meters per second. At that moment in time, he's still on the ground. He's got 6 meters per second coming off the ground. All he has is kinetic energy right here. But then as he goes up and he lands on this shelf up here he's got gravitational potential, but he's not moving anymore. What he's doing is he's transferring all of his kinetic energy into 100% gravitational potential. What I'm proposing is that the kinetic energy at the beginning, when he's on the ground, moving at 6 meters per second upwards, will be equal to the gravitational potential he gets at the top when he has exhausted all of his velocity. That's the strategy I'm using, is at any moment in time, total mechanical energy is equal. It hasn't changed. My total mechanical energy at the bottom was based on pure kinetic. My total mechanical energy at the top was based on pure gravitational potential. And I'm setting those equal to each other. Now let's look at the graphs right below the problems. It asks us to kind of draw the graphs, sketch the following graphs of the gazelle's motion, choose up as the positive direction, okay, ground as the position 0, label any known units. Fantastic. When at time point 0, as far as the y, our gazelle was on the ground. Over time, he went up, and then he came back down. Our velocity in the y direction over time, we started at, this would be 6. At the halfway point, it was 0. And then as he came down, he went to -6. Because we know that when he gets back to his starting point, the magnitude of the velocity is the same, just in the opposite direction. The acceleration over time should be really easy to us. The acceleration is based purely on gravity. So we know -10 should be right here, and we can graph the acceleration. It was all based on gravity, -10. Now, you could probably remember the first couple of weeks of school, this was the hard stuff. Now we look at this and we're like, this is so easy. You couldn't imagine how it was going to get any harder because you're like, wow, that stuff's so hard. Just think one day, this stuff that we do today that you're going to think is so hard, you're going to be like, I remember when I was on energy, that stuff's easy. I wish we could do more of it. Yeah, right. Okay, so let's look at this. What about gravitational potential over time? When he was on the ground, he had no gravitational potential, but he jumps up, gravitational potential peaks, and then he comes back down, lands on the earth, all nice and happy, has no more gravitational potential. Is gravitational potential compared to the y-axis or to the position in y? If he's got 0 y, he's got 0 gravitational potential. As his y goes up, his gravitational potential goes up. The higher you are in relative to the ground, the more gravitational potential you have. His kinetic energy over time, he started out with 6 meters per second velocity. So he started out with a lot of kinetic energy, and then over time it reduced. And then he was at the top of his height. So he had no kinetic energy, but he changed direction. He started coming back down. As he comes back down, he starts getting that kinetic energy again. The kinetic energy is always positive because the velocity is squared. So if your velocity is positive or negative, the squaring brings it right back. His kinetic energy based on his Y position. If he has a 0 Y position, that's where his highest kinetic energy was. So it was here. And as he went higher in the sky, his kinetic energy dropped off. It dropped off because he was slowing down. Now the total energy of the system, total mechanical energy, is conserved. We were moving it from one form to another, but we didn't lose any along the way. So I would say that total energy over time, constant. Imagine I drew a straight line. Total energy based on height, didn't matter what position you are above the ground, you either had more or less gravitational potential, but whatever you lose in gravitational potential, you picked up in kinetic, and whatever you lost in kinetic, you picked up in gravitational potential. So this two, imagine two straight lines, both at the same level. Let me just take a look at this. Wait, why isn't the UG over Y graph not a parabola? Why is it a line? Because my inability to draw a parabola. Don't realize that you've got a person drinking a caffeinated drink, drawing lines is what you would hope that you could take this graph plus this graph should equal this graph. At any moment in time, if you take the amount of gravitational potential and kinetic energy and graph it across time, you should have the same, for this situation, you should have the same amount of energy. So if it's not drawn perfectly, my apologies. The idea is you should see, hey, it's positive, it's going to zero, it's going back to positive, that sort of thing. That's what we should be interpreting from this. So why aren't the graphs the same if you set the formulas for kinetic? So in this scenario, the kinetic turns into UG, right? Right. So why aren't the graphs the same if you, wait, hold on. Well, at the beginning of time, he's on the ground, so he's got no kinetic energy, but he's moving. So he's got no potential because he's on the ground, but he's got kinetic because he's moving. Again, you want to add that maximum K plus 0 potential. At the halfway point, it's all potential, no kinetic. Those still add up. So can you explain that graph? Is it parallel or straight line? Just to make sure, can you explain that graph? That graph? Let me just point and choose which one. I'm not sure. I mean, I see like all different questions. I'll tell you what, put the numbers to it and see what you come up with, okay? This isn't so much I'm gonna memorize what the teacher drew. What we need to realize is it's increasing or decreasing, and it's moving from one position to the other. The UG over Y displacement one, UG, Y displacement one. Okay, if you're on the ground, you've got no potential energy, right? And the more Y you have, which is the higher you have, the more gravitational potential energy you're gonna have. So let's say this is like 1, 2, 3, 4, 5 meters off the ground. The more off the ground you are, the more energy you're gonna have, potential energy. Okay, I'm gonna move on from these graphs because I think too many people are getting hung up on what does it look like and should I draw it like this? Come up with some numbers, you'll be fine. What you need to, you're getting confused by the forest, by the trees kind of thing, whatever that analogy is. We need to just understand that, okay, energy is constant and it's fluctuating from one form to the other. Okay, let's hold on to the concept and not get so much like, oh wait, but when his line went down, it was squiggly, you know, and I drew it in purple. What am I trying to tell you there? Did I draw it in purple? Yeah, that's purple. Okay, let's stay on what's kind of important, and I'm going to kind of guide you in that direction. The sheet was for some reason missing a component of this, so I'm going to draw it out for us. All right, if we have a pendulum, okay, so if I drew a pendulum, I guess I need a drawing tool to draw a pendulum. So this is a pendulum, comes down, and there's a ball on the pendulum. If I pull that ball to the left side, to the far left side, it would be over here now. If I allowed it to fall, it would start to fall. It would go through that middle portion, and then it would be over on the right, and then it would come all the way up on the right. Okay, this is one pendulum, one ball, and it's in 5 different positions. This is position 1, 2, 3, 4, 5. Position 3 is straight down. Okay, position 3 is straight down. If I wanted to graph what energy I have at position 1, here I would say that at position 1, that's when the ball goes all the way up to the left, changes direction, comes back to the right. The fact that it's changing directions means that for a moment in time, it has a 0 velocity. If it has a 0 velocity, it has no kinetic energy. So at position 1, I would say that it has all gravitational potential, UG. And kinetic needs to be 0. So kinetic, I got nothing on kinetic. But at position 2, I'm kind of in between. I'm headed towards the bottom. I'm not at the bottom. I've given up some of my height to swing towards position 3, and I've got some velocity now. So here I would say perhaps I've split the energy, and I've got half gravitational potential and half kinetic, but I still only have 4 blocks of energy. At position 3, I'm as low as I can go. I don't go any lower than position 3. That ball never goes lower. It starts to swing upward again. So now my gravitational potential is 0, where my kinetic energy is at its maximum. It has the 4 bars of energy. And again, the 4 bars is just a number. You could say 4 billion bars of energy, and each bar represents 10,000 joules. Who cares? The idea is I had 4 to begin with, and every step along the way, I only had 4. I didn't get energy. I didn't lose any energy, okay? At position 4, here I'm going upwards. I'm sacrificing some of my velocity so that I can get height. At this point, I would say that my UG and my kinetic energy are back in balance. They both have 2 bars. And then at position 5, I would say, okay, at that place, that's where my kinetic energy, my velocity is changing direction. So my kinetic energy goes to 0 because my velocity goes to 0. And my gravitational potential is back to 4 bars. Here we can see that as we're going through this motion, our energy is fluctuating from one type of energy to another. When the ball changes direction at position 1 and position 5, for a moment, its velocity goes through 0, from negative to positive or positive to negative. It goes through 0. 0 velocity means 0 kinetic energy. The formula is 1/2 mv squared. If v is 0, is 0. Gravitational potential energy, if the height is 0, we're going to call position 3 height 0 because that's as low as it goes. That means I've got no gravitational potential. But as I go higher with a displacement that is greater than that position, that means I'm gaining gravitational potential energy. So I want to look at this as just another example of where we've got something in real life where we're fluctuating between 2 types of energy. We're not gaining or losing, we're simply converting. I've got one more example. It's going to be even a worse drawing than what you just saw. I'm going to scroll this up. All right, so with the spring, what if I had, let's call this like, this is position 1, position 2, position 3, 4, 5. Okay, and then let's call this dotted line the equilibrium. So when the spring is at the equilibrium, that means it's happy, okay? It's where it wants to be, it's chill. If you stretch it beyond that, it's pulling back in. If you compress it shorter than that, it's pushing back out. It wants to end at the equilibrium. And then just for the illustration, we're gonna say there's a ball at the end of the string that we kind of monitor. Or I'm sorry, at the end of the spring. So at position 1, this is my spring, this squiggly is my spring. Here's my ball. We've stretched that spring out. Position 2, that spring is coming in a bit. Position 3, it's right at equilibrium. Position 4, it's come in some. Position 5, it's compressed even more. Here, the spring is moving horizontally. There is no gravitational potential because I have no height here. Everything is moving in the horizontal. If I want to graph each one of these, let's see, how did I do the last one? 1, 2, 3, 4. Let's see, 2 would be here, 3, 4, and 5. At position 1, I've either got spring potential or kinetic. Well, when the ball is at the furthest out that it goes, this is where it's going to go from moving to the right, back moving to the left. And we know that the velocity is going to go through 0. If the velocity is 0, the kinetic energy is 0. We have 100% spring potential. So let's do our 4 bars for all spring potential. The spring is upset. It's like, hey, I want to be back at equilibrium. I'm pulling as hard as I can. I'm bringing it back in. At position 2, it's been pulling on it. So now it has a velocity going to the left. And we have less spring potential because now it's getting closer to equilibrium. The spring is getting happier. It's starting to chill out a little bit. So we're going to say, how about we've split it? Okay. That energy is moving to kinetic. At position 3, when it's at equilibrium, the spring isn't pulling or pushing anymore. It's like, this is right where I wanted to be. This is my happy place, right? So the spring potential, sorry, let me fill those in. The spring potential goes to 0, where the kinetic energy is going to be its maximum. Because this is the moment that the spring goes from pulling it, and as soon as you pass the equilibrium, the spring starts to push it. So this is as fast as the ball is going to be moving right before the acceleration switches directions. Because the acceleration initially was to the left to move the ball to the left, as soon as it passes equilibrium, the acceleration, the net force is going to the right. And that's going to slow the ball down to 0 and start pushing it to the right. Okay, we get the idea. Position 4. Here we're kind of in the mix, in the middle. Spring potential. Why am I saying gravity? That's just wrong. Spring potential, that is a big U, little s, just for those that can't read my handwriting. We're back to split. And position 5, this is where the spring is completely compressed. The ball is going to go from moving to the left back to moving to the right. So the velocity is changing direction. It goes through 0. So the kinetic energy would be 0. This is a K. And then the spring potential would be at its maximum again. We'll just call that 4 bars for this illustration. Here, again, a different example. We're showing a spring where we've got spring potential and kinetic energy, and then the compression or the expansion or the stretching of the spring creates or has and housed the source of, whatever you want to say, the spring potential energy. As it causes movement, that spring potential then is converted to kinetic energy. This is just another way to illustrate, okay, this is the concept we're trying to get across. It's not, how was it drawn or anything. It's not about the 4 bars. It's just like, okay, I understand energy is fluctuating from one form to another. And in a closed system, in an isolated system, here we can see spring potential to kinetic. In the previous one, we can see gravitational potential to kinetic. Just trying to make it easy to begin with. But don't worry, I'll make it hard. I mean, I won't make it hard. The problems are going to make it hard. All right, so we've done that. Let's go into the second one. So this is the second attachment in Canvas. I'm going to highlight for you the things that are important, the things that are not important, we won't dwell on. I mean, you can dwell on them if you want to, but I mean, seriously, I'll tell you what's important. The definitions here are good. Let's see if I can actually get a drawing tool going. So these definitions are good. As long as there's no external forces on a system, the total amount of energy remains constant. Constant means it's conserved. Energy cannot be created or destroyed. It can change forms, so the total amount is constant. Total amount in the world is constant. The total amount in your system, we may see some fluctuations on, but the world is constant. And we're going to focus on mechanical energy of the system. Mechanical energy being kinetic, gravitational potential, and spring potential. All right, I'm going to drink of this. Okay. Number 1 is going to walk us through this problem, tell us everything to do along the way. So just hang on. You get to see some ugly art again. I know. It's exciting for me too. All right, so draw a picture of Tarzan standing on a 20-meter high cliff. All right, so we've got, there's the cliff, goes down, and then there's the ground. It said this is 20 meters high. We've got Tarzan standing up here with his big head. And of course, he had long hair, right? So Tarzan, there we go. More like a troll. I'm like totally drawing a troll here, right? So he wants to swing off the vine to the jungle floor below. All right, so then we've got, here's the source of the vine, and then here's the vine he's going to grab a hold of, and he's going to swing down. When he swings down, I'm going to dot it, just saying, okay, this is when he swings down. He'll be down here, and his hair is still like real troll-like. Okay, you got to make fun of the people with hair because I had hair when I was Tarzan's age, right? Some would say. Okay, there's our picture. Not much more I can do about that. Draw an LOL diagram. Okay, an LOL diagram is just saying, okay, I'm going to graph the energy I have at the start. And then in the circle, I'm going to put what in this system. You put that in the circle, and then you draw the graph of the energy at the finish of the experiment or whatever we're looking at, okay? So LOL diagram, it just helps you visualize what's going on. In this case, at the start, we have what? He's up on a cliff, so he's got gravitational potential, UG. They didn't say anything about him running to the vine, so I'm going to say no kinetic energy. At the end, when he swings down to the ground, that's where he's given up his potential, his height, for velocity, kinetic energy. And then what's in this system? There's some UG and there's some K. Now, I'll admit to you, the only time I ever draw a LOL diagram is when I'm doing this worksheet. That's it. But the way I understand things and the way that works for you can be completely different. If the test allows you the time to do this, fantastic. If the practice work definitely allows you the time, if this helps you understand and makes things click, do it. But am I saying you have to do that every single time? Oh, heck no. You will not see me ever do another LOL diagram after this moment in time unless you play this Zoom back, because I'll put this up probably tonight or tomorrow. Okay. And if you're watching that, hey, it's not today for you. It's like some other day. I'm just kidding. All right. Write a conservation of energy equation and substitute in the formulas for the individual forms of energy. What it's saying is we started with gravitational potential, and at the end, we finished with kinetic, and we're hoping that those two are equal to each other. That's all that's saying. Then it says now substitute in your variables. Well, that just means that gravitational potential is mgh, and kinetic is 1/2 mv squared. Substitute for individual forms of energy. Okay, I guess we want to rearrange solid force. Wait, right? Formulas for, okay. Solve the equation for the requested value. Okay, this is where I get to solve it for the requested value before putting in numbers. So I'm going to bring that down here, and I've got mgh is equal to 1/2 mv squared. The m's cancel. We're looking for v. Aren't we looking for v? Yeah, we're looking for v. I want to multiply both sides by 2 to get rid of the half. And then I've got to root both sides so that I get the square root of v squared would be v, that sort of thing. That would give me 2gh square root of is equal to v. Again, I multiply both sides by 2 to get rid of the half on the right, and then square root so that it solves for just v. Then in E, it says substitute the numerical values and calculate. Okay, great. Square root of 2 times 10 times 20. 2 being part of my formula. G is gravity. Gravity's 10. And the height, they told us at the beginning, was 20. And that's equal to velocity. The square root of 20 times 20 is 20 meters per second is my velocity. This was set up so that it gave us, kind of broke down, hey, draw a picture, draw the graphs of your energy and how it's changing. Now put together your formula, now rearrange your formula, now solve. It broke down the steps one at a time. If there was any confusion along the way, it helped isolate us from that. Okay, I'm going to go on to the back part of this page. There's a number 2 and a number 3. We can do these rather quickly, and then we're going to go on to the last problems that I think we have to do 1 or 2 together. We have to do at least 2 together. I think it's 2. So let's get through these 2 that are fairly straightforward and then see what happens. All right, Tarzan, in an attempt to escape a gazelle who's gone mad, is running on the jungle floor. Okay, now Tarzan is like really upset because his hair is like gone crazy. And he is like running for his life. Let's say he's going this way at velocity equals 10 meters per second. And he sees this vine. He's going to grab it, and he hopes that it will take him up 10 meters. He's going to trade his kinetic energy for gravitational potential. And we need to determine, can he get up 10 meters? Well, his gravitational potential in the beginning will equal his kinetic energy at the end. His gravitational potential is mgh. That's equal to 1/2 mv squared. Again, the masses cancel out. I got those backwards, didn't I? All right, let's pretend I didn't write it that way. His kinetic energy at the beginning is equal to his gravitational potential at the end. 1/2 mv squared is equal to mgh. It's the same thing. I just feel better about writing it in the order that's relevant, right? Masses cancel out. I'm going to divide both sides by g so that we can solve for h. We want to see how high will he get based on the velocity that he has. That would give me v squared over 2g is equal to the height. All right, let's put some numbers to it. He was running at 10 meters per second. 10 times 10, or 10 squared, would be 100. Divided by 2 times g, which would be 2 times 10, which is 20, equals the height. That means 5 meters is as high as Tarzan's going to get. Bad day for Tarzan, good day for the gazelle family, right? They just got some dinner. He didn't have to get higher, he would need to run faster, right? Whatever he needs to do to get faster, have more kinetic energy so that he'll have more gravitational potential. That is a crazy drawing of Tarzan, by the way. I know, it's one of those days. Let's look at number 3. A pinball is resting on a spring, which is compressed by 0.3 meters, ignoring friction. How fast will the pinball be traveling, which is launched to the spring? All right, if you ever play pinball, you like pull back this little hammer thing and it compresses a spring. And when you let go of it, that spring then like pushes out against a little metal ball, and that metal ball then has velocity and bounces around off of things, right? So here, there's no vertical, right? Pinball machines are pretty flat. I mean, they might sit at a little bit of an angle, but that's for a different reason. All right, so let's ignore that portion of it. Just say, hey, whatever energy is going to start with the compression of that spring is going to be transferred into velocity, right? So we're going to start with spring potential, and then we're going to translate that to kinetic energy. Spring to potential was 1/2 kx squared. The k is the spring constant. The x is how far is the spring either stretched or compressed from its equilibrium happy place, okay? And that's equal to 1/2 mv squared. We know that's kinetic energy. The 1/2s cancel, right, because they're on both sides. And we're wanting to do what? How fast? We're looking for velocity. So we would say that that is k times x squared divided by mass. If we square root that, that is equal to velocity. I basically divided both sides by the mass to bring the mass to the other side, and then I square rooted it so it would be equal to velocity. This will tell us what the velocity is. Let's just simply put this together, see what the math is. We would have the square root of, what is k? 60 times x squared. X is 0.3. 0.3 squared divided by the mass of 0.05. All right, let me get my fancy calculator out. 60 times 0.3 squared is 5.4. I'm going to divide that by 0.05. And then that gives me 108. I'm going to take the square root of 108. And I get 10.39. Okay. 10.39 meters per second equals the velocity. Here it's just a simple transfer of energy from one form to another. Okay, now that we've done that, we've gotten through 2 of the 3 worksheets, packets, whatever, things that have notes for us and practice problems for us and helps us kind of see what's going on. Let's get into the last one. Let's make sure that we can get all the way through where our goal is for the day. Let me bring this one up and zoom it in a bit. This is the one that I think had some areas that we were going to kind of skip over. I'm going to hit the highlights to make sure that you have a good understanding of what we're doing. Oh, let me see. On these problems, we never have to find the spring constant. Yes, you could. You could have to find the spring constant, but you would have had to have been given, if you were given everything but everything that you had before, take away the spring constant and you were given velocity, you could have, right? So yes, any of the variables you could have to solve for, but you would have to be given enough information to do so. Just to clarify, when setting UG equal to K, it is doing it because the beginning kinetic energy is equivalent to the ending UG energy. That is correct. Yes, that was well stated too. Let's see, did I miss anything else? No, I think I'm good. Okay, those are good questions because it shows, I mean, you're thinking about it, you've got to process this. The good thing is once you understand it, the problems aren't bad. They're challenging like puzzles, but they're not impossible. Before you get it, I mean, you want to sit down with like a sugary drink and, you know, take a nap between each problem. I get it. I mean, that's what I used to do. Let's look at this. All right, you throw a tennis ball up in the air. What can be said about each of the following as the tennis ball, let's start with, moves upward? I need my drawing tool. When it moves upward, well, we know gravitational force is equal to m times g, which is equal to mass times 10. I would say that about gravity. As the ball goes up, the displacement is positive because it's going up. Work done by gravity, well, gravity is downward. Displacement was upward, so I would say the work done by gravity would be negative. As the ball goes upward, it's going to slow down and approach 0. So I would say kinetic energy, you're going to lose kinetic energy as it goes up. But as it goes up, it's gaining height. So that means you're going to gain potential energy. But the total mechanical energy is going to be held constant. Now, as it moves downward, gravitational force hasn't changed. It's still gravity, mg, or m times 10. The displacement as it comes down will now be negative. Work done by gravity, well, gravity's pulling down, displacement is down, so now work by gravity is positive. As it goes down, it speeds up, so kinetic energy, you're going to gain kinetic energy. Gravitational potential, as you go down, you lose height. So if you lose height, you're going to lose potential energy, but your total mechanical energy is still held constant. Okay. Now, this next little paragraph is good information. Gravity and springs exert what is known as conservative forces. What does that mean? Oh, well, the next sentence starts with, this means that there's a direct relationship by the work done by the force and the change of potential energy of the system. I like to say that it means you're not losing any of the mechanical energy within your system to friction. Friction will rob you of mechanical energy. Let me give you an example, okay? So actually I prefer to, we've been sharing for a long time, so let's do it like this. You ever go to the park, maybe when you're little, but you went to the park and you saw that slide and you really wanted to ride that slide down, right? So you climbed up all those steps. Think about when you're way little and those steps were way big. You get to the top of the slide and then you slide down. And one slide, maybe when you got to the bottom, it was going so fast, you went right off the end. You had to like take a couple of steps just to keep from falling, right? Because all that height was turned into all that velocity at the bottom, right? So then on a cold day, you wore your jeans to the park instead of those athletic shorts that made you go really fast, right? The slick ones. Today, you wore your jeans to the park because it's cold out. You climb up that slide and you're like, hey, mom, watch this, right? Because every time you're gonna do something cool, you got to call out to someone for them to watch it. And when you slide down the slide, halfway down, you like come to a stop. And you're like, what? And and you start scooting yourself to get yourself moving. We've all been there, right? If you've ever been on a slide, you've been on that one slide that you had to like, come on, what's the deal? Why did my gravitational potential energy not transfer into velocity? Because friction came along and took it away from us. So what we could say is, what we could look at, now I'm going to go back to the share because I need something to write on. Share, seriously, share. There we go. Let me scroll this up. We're going to skip all this because this is just like things to make you tired. We're going to go this. Practically, what does this mean? Okay. What we're going to say is, at the top of the slide, you had all the gravitational potential you could get. So you expect to have that as kinetic energy on the bottom. But on the bottom, you may have had something less. You actually ended up with something much less. So what if we said the actual energy at the bottom minus the expected energy from the top? That will equal the work done by friction. If we calculate all the energy that's at the top based on height, and then we look and we calculate all the energy at the bottom based on velocity, and we compare the two. If we take what we actually got at the bottom, which will be a smaller number if friction is present, and we subtract the expected from the top, we're going to see the work done by friction will be a negative number. And we know it's a negative number because friction is always in the opposite direction. Friction's a force, and it's always in the opposite direction of motion. So friction's work should always be negative because the force is pointed in the opposite direction of motion. Okay, this is how I want you to think about it. What I actually ended up with minus what I started with or what I expected I could have had at the bottom, that's equal to the work done by friction. Now, yes, we can do it in a fancy formula because you asked. Let's look at this fancy formula right here. I'm going to rearrange it to something that makes a little bit more sense, not a lot more sense, but a little bit more sense. Here, I'm going to say, what if we said that it was K plus UG plus US? This is total mechanical energy, whether it's kinetic, gravitation, spring, whatever, total mechanical energy. Let's put that in brackets. And what if we subtracted the initial total kinetic energy, K naught plus UG naught plus US naught, and said that that is work done by non-conservative forces. Friction's a non-conservative force. So we're just saying that our final total mechanical energy minus our initial total mechanical energy is equal to the work done by non-conservative forces. That is our fancy way of doing it so that you've got a nice, beautiful formula. But when we're thinking about and processing it in our mind, let me just scroll back up. The actual minus the expected was the work done by friction. Now, it does give us a couple of cute little bullet points. If no non-conservative forces are present, then the work done by non-conservative forces is zero because no non-conservative forces are present. But if there are non-conservative forces present, then the total energy of the system does change. It goes down. The system energy goes down, but the world energy is still there, right? You lose energy to friction. Friction's heat. It's just like out there. You're not going to gain that back within your little system of Tarzan or for whatever's going on. They're not going to be like, well, the heat that I gathered along my way helped speed me up. It's not going to happen. Okay. All right, let's see what else this shows us. Let's see if there's anything important. Nope.
So Watley,
Yeah, what's up?
with that formula, like, can we take that initial energy and final energy as like a change in energy formula?
Yes.
Okay.
Yes. Now, you're going to use parts of it, though. You can use it the way it's written right now in purple on your screen. And what you would find is if there's no non-conservative forces, you're going to end up with zero because your initial energy, total energy minus, I'm sorry, your final total energy minus your initial total energy. If you've conserved all of your energy, it's zero because it's the same amount. Now, what you could do is use parts of it just to look at work and say, okay, I want to look at the change of just kinetic energy. That's work. Or I want to look at just the change of gravitational potential. That's work. But if you look at total energy compared to total energy, if there's no non-conservative forces, the subtraction is just going to give you a 0. Okay, let's let this sheet not confuse you. There is a blank page here. You have to go beyond the blank page. I'm sorry, I didn't know it was there till this morning. But then this brings us into sample problems. Now we have like 20 minutes left of class, 25 tops. We have 2 problems we're going to do together. And then on the next page, I'm going to give you number 3 to do. That's number 3. 1 problem is what I ask you to attempt between now and before next class. Or actually, I asked you to do it this week. Okay, now, does that mean it's going to be easy? Well, I mean, come on now. Have you not met me before? I don't know if you can see my screen, but this is my work for number 3. I know, right? Somebody's trying to take a screenshot. All right, I moved it away. Just kidding. I'm going to post this work, but I really ask that you do your best to attempt it first. Only peek at the key for guidance if you need it, okay? But do your best to attempt it first. Let's go back up to number 1 so we can build our confidence with something that's really not that challenging. We have a skier goes down all right, so the mass of the skier is equal to 50 kilograms. And then we've got the height. I don't know how to spell height, apparently. 78 meters. Okay, so this is a variety of slopes. If we want to draw this, here's the skier up here. She's so happy. And then here's the slopes. It goes like this, and then there's the bottom. And then here's our skier at the bottom. She's observed to be going 30 meters per second at the bottom. So we have 30 meters per second at the bottom. And we know that up here, she's 78 meters high. How much work is done by friction? Well, let's take a look at how much energy is at the top, how much energy is at the bottom, and let's look at the difference. This is just like number 8D in last night's homework. 8D asked us to determine the amount of work done by air resistance. There, if we looked at the 8A and 8C, we would have seen the energy in the system at 2 different spots, and then we subtract them. That's why I was like, hey, this is going to lend itself to today's lecture. 8D, that this is where you're listening. Okay, cool. At the beginning, it's all about gravitational potential, which is mgh. In this case, that would be 50 times 10 times 78. And my handy dandy calculator, I've got what, 50 times 10 times 78. I got 39,000. So she has 39,000 joules of energy chilling up there. When she gets at the bottom of the hill, she's got no more height. She's got all velocity. That is kinetic energy. That's 1/2 mv squared. 1/2 times mass of 50 times 30 squared. 0.5 times 50 times 30 squared equals 22,500 joules. 22,500 joules. From here to there, we've lost some energy, quite a bit of energy, like 16,500. Because if we take our actual 22,500 minus our expected of 39,000, we get 16,500 negative, 16,500 joules. And that is the work done. That is the work done by friction. That's how much energy was lost. I see something came in the chat. Let me see. So our air resistance and force of friction, non-conservative forces. Yes, think of air resistance as friction from the air. Air resistance is basically friction from the air. So do we need to add the negative sign or can we keep it positive? Well, if you do the subtraction, it's going to be negative. 22,500 minus 39,000 is negative. So you should get negative. The work done by friction is always going to be negative. Don't forget that. It's going to be negative because the force of friction opposes motion, and work by definition is negative work is forces in the opposite direction of the displacement. Okay, that was a good warm up. I mean, it's a good problem. You're like, okay, I can handle these. So stop there, right? No. Number 2 is going to make you question, why did you not take on level? No, I'm kidding. This is so much better than on level. Yeah, right. Okay, I'm just kidding. No, I'm not. All right. Ralph the Wonder Llama begins from rest. All right, we've got initial velocity equals 0 meters per second. At the top of a 10-meter tall playground slide, okay, they marked 10 meters for me. The coefficient of friction between Ralph and the slide is 0.2, okay? We've got this equals 0.2. How fast will he be going at the bottom of the slide? All right, right here, we want to know what velocity is equal to. At the top, this is all UG. At the bottom, this is all kinetic. Okay. I'm going to have a change of energy. I know that a change of energy is work. Work is force times displacement. Okay. I know that the force involved here is I've got gravity pulling me down. I have friction resisting me. So I know if I'm thinking about it, okay, work is a change of energy. If I can figure out what the change of energy is, I know kinetic energy is going from 0 to something. Okay, that's a good thought. Let's hold on to that one. If kinetic energy initially is 0 because he's not moving at the top of the incline, but he is moving at the bottom, we're going from 0 to something kinetic energy. Work is a change of energy. We have a change of energy. Now, work is also force times displacement. The forces involved here, there's a component of gravity pulling me down. There's friction resisting that. That's my forces. And then I've got a displacement. So I need to figure out what are my forces and what is my displacement, and then we can solve this, right? Awesome. Let's do it that way. Okay. I mean, you kind of should follow me because I've already done it twice today. So I kind of know what I'm doing. A little bit. All right. Don't trust the crazy guy in the purple sweatshirt. It's a hoodie, not a sweatshirt. All right, so what do we have? How do we get that hypotenuse? Well, we know that the sine of 30 is equal to the opposite 10 over the hypotenuse. Okay, awesome. Well, I can rearrange this equation and say that the hypotenuse then is equal to 10 over the sine of 30. I just multiplied both sides by hypotenuse and divided both sides by sine of 30, otherwise known as a shortcut that you can swap those. Didn't you say we always use cosine, never sine? I never use the word always. But what I have is, see the 30s right here and see this 10 right here? Those are the only two numbers I have. And sine is opposite over hypotenuse. Cosine is adjacent. I don't know what the adjacent is, so I can't use cosine. But what I would always say well, no, I always say never say always. That's a good one, isn't it? I know, right? I'm entertaining two people. The rest of you just want to stab me. I get it. That's cool. It's not cool that you want to stab me, but it's still entertaining somewhat. All right, sine of 30. And I'm going to take 10 divided by that sine of 30. Sine of 30 is 0.5. 10 divided by 0.5 is 20. So that means the hypotenuse equals 20 meters. It means this guy right here is 20 meters long from top of the incline to the bottom of the incline. Oh, by the way, if you're going to the homecoming game, I'm going to be in the section 200. I'm in the upper deck. So take a look around. If you're going, wave, say hi. I'll have 2 kids and a gorgeous wife with me. So it's my wife, not somebody else's gorgeous. I'm just saying. Okay, we'll be there. All right, let's go back. So we've got the distance now. Now we need to get the forces, right? So let's take our free body diagram of what's this, a llama? Of a llama, and draw him as square, like straight. So his force of gravity would be going this way, right? So a component of it is going down, a component of it's going to the right. We have force normal going up, we have force of friction going to the left. We know that this is 30 degrees is the incline, okay? Let's see, if this is mg, then the bottom part would be mg sine of 30. And then the vertical component would be mg cosine of 30. We know that he's not accelerating up or down. He's moving left to right, in this case, the way it's drawn. So the force normal is balanced with the force of gravity, the vertical component of the force of gravity. So this would be mg cosine of 30. And then we know force of friction is basically the coefficient times mg cosine 30, because it's the coefficient times force normal. So that part's not new. That part's not new. We just took a test over 2D forces. So that should be either like, yeah, I got it, or yeah, well, you should have seen my test. You know I didn't get it, which is cool. You need to learn this stuff. It builds. I'm just saying. Now, my summation of forces. Summation of forces is going to be equal to what's pulling me down the ramp? Mg sine 30. Mg sine 30. What is resisting me going down the ramp? Well, that's based on friction, which would be coefficient times mg cosine of 30. Now, I don't know what mass is, but I know the coefficient, I know g, and I know the sine of 30, and I know the cosine of 30. Let's clean this up with some numbers and do the best that we can. Don't know m, but g sine 30, that is 10 sine 30. In my calculator, I get 5. So here I get 5 times mass minus the coefficient. All right, so what is the coefficient? 0.2? 0.2 times 10 is 2, right? So we would have 2 cosine 30 gives me 1.73. 1.73 times mass is my summation of forces. And if I have 5m and I subtract 1.73m, that should give me 3.27m. Yeah, that adds up, right? So my summation of forces is 3.27m. Why did I do that again? Well, I'll tell you why. Work is equal to force times displacement. So my work will equal 3.27 times m times the displacement of 20. All right, if I multiply that 20 in times 20, I'm using a calculator so I don't make silly mistakes, I get 34.64. Why does that seem weird? 1.73 times 20. 34.6. Yeah, 34.6. Work equals 34.6, let's say m, because it's still times mass. Yes.
3 times 20 is 60.
What is going on with my... Oh, you know what? I'm typing in 1.73 again. Yeah, I'm looking at the wrong place. You're totally right. And thank you for being the only person that spoke up, and everybody else is like, what is he talking about? 3.27 times 20, 65.4. Yeah, that's way better. All right. 65.4. Shows you that at the end of the day, I can't run a calculator. All right. Work is 65.4 times mass. That's the work being done. Okay. Now, work is also equal to a change of kinetic energy, right? Now, the kinetic energy started out as my initial kinetic energy, or my final kinetic energy minus my initial kinetic energy, right? That is a change of kinetic energy, final minus initial. My initial kinetic energy was a big fat 0, right? Wasn't moving, velocity was 0. So if the initial kinetic energy was 0, that goes away. My change of kinetic energy, my work, is equal to the kinetic energy. Because it's final minus initial. Initial is 0. Minus 0 doesn't change anything. So in this case, because the initial was 0, the work is just equal to what the final is. Well, work is equal to kinetic energy, and kinetic energy is equal to 1/2 mv squared. We said that work is equal to 65.4 m, and we said that work is equal to 1/2 mv squared. Let's set those two equal to each other. 65.4 times m is equal to 1/2 times m times v squared. The m's cancel out. If I multiply 65.4 times 2 to get rid of the half, I get 130.8 is equal to v squared. I'm going to square root that. I get 11.44 once I round. 11.44 meters per second is equal to my velocity at the bottom. Work is force times displacement. Work is a change in energy. You can set those two things equal to each other because they're both equal to work. I'll give you a second to digest that. And then we need to move on to part B of this question. And then that will be about the time they start screaming at me over that speaker saying who needs to be dismissed. All right, the coefficient of friction between Ralph and the ground is 0.3. So now Ralph is moving, he's trucking at 11.44 meters per second. He's on flat ground, and that flat ground has a new coefficient of friction, of course. Why wouldn't it not have the same? Who knows? This coefficient of friction is equal to 0.3. Okay, let's draw a free body diagram for Ralph's current position. I tell you what, let's change colors for part B. So let's erase this. And maybe by changing color, it'll be easier to visualize what's going on. So 0.3. And it's saying, how far from the end of this slide will Ralph come to a stop? Again, work is force times displacement. It's asking us for the displacement. And we know that Ralph doesn't have a rocket on his back. The only force acting on him at this point is friction. All right, there's no more slope, there's no more component of gravity. Let's draw a free body diagram. Ralph, at this point right here, he's got mg going down, he's got mg going up, and he's got the force of friction, which would be the coefficient times mg. Okay, so the force of friction is his only force, and that is equal to the coefficient times mg. And if we just want to hurry up and get the numbers in because it makes us feel better, well, we know g is 10, coefficient is 0.3. So wouldn't we say it's 3m, 3 times m is the force of friction? And we're looking for the distance, so the distance is kind of question mark. So we know the work would equal force times displacement, which is equal to 3 times mass times distance, right? We just need to solve for d, but we got that pesky m in there. Okay, let me ask you this. Separate question, okay? If it takes a certain amount of work to, let's say it takes 5,000 joules to change, to move a car of certain mass from 0 to 20 miles an hour. If that takes 5,000 joules, how much, is that the same change of energy to go from 0 to 20? Is that the same change as from 20 to 0? Okay, so if we defined it and said, hey, it's 5,000 joules to move this car from 0 to 20, wouldn't it be 5,000 joules to go from 20 to 0? Because it's the same change of energy, 0 to 20, 20 to 0, right? Doesn't that make sense? Okay, so we were able to determine how much work it took from Ralph to go from 0 to 11.44. So wouldn't that be the same amount of work it takes for him to go from 11.44 to 0? The amount of work to get Ralph to go from 0 meters per second to 11.44 meters per second is right here. The work to go from 0 to 11.44, we said was 65.4 times the mass. Isn't that the same amount of work to go from 11.44 back to 0? It's the same change of energy. He went up in kinetic and now he's going to come back down in kinetic, right? So we should be able to say that 65.4 times m is equal to 3 times m times d. Because we already know what the work is, and we know it's defined by saying force times displacement. If we do that, the m's cancel. We divide both sides by 3. And let's see, 65.4 divided by 3 gives me 21.8 equals my distance. This one is one that you work on and you go eat some crackers and you come back and work on, you go take a nap and you come back and work on, because you're going to be away from the problem and you're like, wait a minute, I did have the work. Why didn't I think of that before? And you take off running, you go work on it some more, then it ticks you off and you come back to it. But when you can do a problem like this, you can do any of the problems. Now, that's why I bring up number 3. This one, you better draw a picture. I'm serious. You better draw a picture. This is a very challenging problem, but this is what changes the students that get the 60s to 70s and come back and retest and get the 85s from those that get the 80s and 95s and say, retest? Why do I want to do a retest? I do good on the tests. Work on it, try it, email me, show up to tutorials and tell Mr. Hennessy and Miss Doyle that they need to explain it better because Watley totally messed you up. I'm just kidding, don't say that. That would be embarrassing to you. I'm kidding, that'd be embarrassing to me. All right, so this is where we were. Let me back this out. So if anybody wants to take like a screenshot and have all the info all at one place, I'll let you do that. All right, there's your screenshot time. Don't forget, you've got number 3, the Wile E. Coyote problem. You've got the concept check. Both of those, we need to get those done sooner than not. The Wile E. Coyote, I would start sooner than not, so that way you can kind of work on it, come back to it. Work 1, 2, 3, and the homework from last class. All that stuff needs to be done. And don't email me Sunday night at 11:45 for help, because I'm in bed and nobody wants that. So work on it earlier so you can get more help. The FRQ is going to be on Monday.